Welcome to Learn Chemistry Together. This video is about boron and phosphorus reagents in organic synthesis. Chemists soon learned to make dyestuffs, which were both cheaper and better than naturally occurring dyes. Synthetic drugs have saved innumerable lives and spared mankind a great deal of suffering. The synthesis of vitamins and essential amino acids used as food additives have improved our diet, especially in developing countries. Plastics, which are part of our daily lives, are products of organic synthesis on a large scale. Chemicals for controlling microorganisms, insects, and weeds have saved millions of lives and reduced starvation. For these objectives and the similarities, new synthetic methods have been developed since 1830s. Boron reagents. Herbert C. Brown, who was professor at Purdue University, had developed new reagents containing boron. He joked about his initials H, C, and B, which are also the chemical symbols for hydrogen, carbon, and boron, the elements contained in the compounds, which he studied. One of his reagents is sodium borohydride, which has become the reagent of choice for reduction of carbonyl compounds, Figure 1. He had also modified the borohydrides into reagents for highly selective chemical transformations. In addition, Brown had introduced an entirely new class of compounds, the organoboranes, obtained by reacting diboron with olefins, Figure 2. Thanks to the work of Brown and his co-workers, the organoboranes have become the most versatile reagents ever created in organic chemistry. They can be used for reductions, rearrangements, and additions, and have opened up a range of new possibilities for linking carbon atoms to each other. The Wittig reaction. George Wittig had been professor in Freiburg, Tübingen, and Heidelberg, and was professor emeritus. He had developed new synthetic methods of considerable importance and had studied reaction mechanisms. His most important achievement was the discovery of the rearrangement reaction, which bears his name. In the Wittig reaction, Figure 3, an organic phosphorus compound with a formal double bond between phosphorus and carbon is reacted with a carbonyl compound. The oxygen of the carbonyl compound is exchanged for carbon, forming the product as an olefin. This method of making olefins has opened up new possibilities, not the least of which are for the synthesis of biologically active substances containing carbon-to-carbon double bonds. For example, vitamin A is synthesized industrially using the Wittig reaction. Brown's and Wittig's results have opened up new vistas in organic synthesis and highly stimulated the further development of their science. Their methods were rapidly introduced not only into chemical laboratories, but also into elementary textbooks and laboratory courses. Thank you for watching. Click follow or subscribe for supporting this channel.